Welcome to this presentation on engineering physics. Engineering physics applies the laws of physics to design and improve real-world systems. Engineers use ideas such as forces, energy, materials, waves, and electricity to create machines, structures, and technologies. In this topic, we explore how physics principles are used to solve engineering problems. Scope of engineering physics in the A-level specification, role of physics in engineering design and problem-solving, key quantities and units used in engineering physics, links between engineering physics and required practicals. Engineering physics focuses on how core physics principles are applied to real engineering problems. It builds directly on earlier mechanics and materials topics and develops an understanding of how materials behave under load, how engineers select materials, and how safety and performance are balanced in design. Students are expected to understand stress, strain, Young modulus, elastic and plastic behavior, and the use of safety factors, all within realistic engineering contexts. This topic links theoretical physics with practical design decisions, such as choosing materials for bridges, aircraft, or buildings based on stiffness, strength, and density. Physics underpins all engineering design by providing predictive models that describe how structures and materials respond to forces and environmental conditions. In engineering physics, students explore how abstract concepts such as force, stress, and energy are used to make practical decisions. For example, when designing a bridge, engineers must calculate the stresses in supporting cables and beams to ensure they remain within safe limits. Physics allows engineers to predict deformation using strain and Young modulus, ensuring that structures do not bend excessively or fail. Another critical role of physics is optimization, where competing factors such as strength, mass, and cost must be balanced. In aerospace engineering, low density and high stiffness are essential, leading to the use of aluminium alloys or carbon fiber composites. Engineering physics relies on a small set of fundamental physical quantities that describe material behavior under load. Stress is defined as force per unit cross-sectional area and is measured in pascals PA, where 1 pascal equals 1 Nm squared. Typical engineering stresses are very large, often quoted in megapascals, MPa. Strain describes deformation and is defined as extension divided by original length, making it a dimensionless quantity. Young modulus, measured in pascals, is the ratio of stress to strain in the linear elastic region and represents material stiffness. Density, measured in kilogram m cubed, is also crucial in engineering design, particularly where weight is a limiting factor. The engineering physics topic is closely linked to the determination of Young modulus. This practical provides experimental evidence for theoretical relationships between stress and strain and develops essential laboratory skills. Students measure the diameter and original length of a wire, apply known loads, and measure extension using a micrometer and ruler or vernier scale. From these measurements, stress and strain are calculated, and a stress-strain graph is produced. The gradient of the linear region gives the Young modulus. Tensile stress, definition, equation, and engineering meaning, tensile strain and deformation of materials, Young modulus and material stiffness, stress-strain graphs and interpretation. Tensile stress describes how internal forces develop within a material when an external force attempts to stretch it. It is defined by the equation sigma equals Fa, where F is the applied force and A is the cross-sectional area. This relationship explains why thin wires experience greater stress than thick ones under the same load. In engineering, stress is a critical parameter because excessive stress can cause permanent deformation or fracture. For example, steel suspension cables on bridges are designed with large cross-sectional areas to reduce stress and increase safety. Tensile strain measures how much a material deforms relative to its original length when subjected to a tensile force. It is defined as epsilon equals LL, where L is the extension and L is the original length. Because strain is a ratio, it has no units. Strain provides a normalized measure of deformation, allowing engineers to compare materials of different sizes. For example, a long cable and a short rod may extend by different absolute amounts, but strain reveals which experiences greater relative deformation. In engineering design, limiting strain is often as important as limiting stress, particularly in structures where excessive stretching could cause misalignment or failure of connected components. Strain is typically very small, often of the order of 10 cubed or less in elastic materials. Young modulus is a fundamental material property that quantifies stiffness. It is defined as the ratio of stress to strain within the linear elastic region of deformation, E equals sigma. A high Young modulus indicates a stiff material that deforms very little under load, such as steel, while a low Young modulus indicates a more flexible material, such as rubber. Young modulus is independent of sample dimensions, making it a true material constant. In engineering, stiffness is crucial where shape and alignment must be maintained, for example in machine components or structural beams. Determining Young modulus experimentally involves measuring stress and strain and finding the gradient of the straight-line section of a stress-strain graph. Stress-strain graphs provide a visual summary of how a material responds to increasing load. The initial straight-line region shows proportional behavior where stress is directly proportional to strain and Hooke's law applies. The gradient of this region is the Young modulus. Beyond the limit of proportionality, the graph curves, indicating non-linear behavior. The elastic limit marks the maximum stress for which the material returns to its original shape when unloaded. Past this point, plastic deformation occurs, meaning permanent extension remains. Many metals show a yield point, where strain increases rapidly with little increase in stress. The ultimate tensile stress represents the maximum stress the material can withstand before necking and eventual fracture. Elastic and plastic behavior of materials, energy stored in deformed materials, safety factors, and engineering reliability, material selection in engineering applications. Elastic behavior occurs when a material returns to its original dimensions after the applied force is removed. This behavior is essential in many engineering applications, such as springs and suspension systems. Plastic behavior, in contrast, involves permanent deformation once the elastic limit is exceeded. Engineers must understand the transition between these behaviors to avoid structural failure. For example, aircraft wings are designed to flex elastically under load but must never enter the plastic region during normal operation. Plastic deformation can be useful in manufacturing processes such as forging, where materials are intentionally reshaped. Stress-strain graphs allow engineers to identify safe working regions and understand how materials respond under extreme conditions. When a material is elastically deformed, energy is stored within it and can be recovered when the load is removed. This elastic energy is equal to the area under the stress-strain graph up to the elastic limit. For a linear elastic material, the energy stored per unit volume is given by 1/2. In practical terms, this energy storage is exploited in springs, shock absorbers, and energy damping systems. Engineers must also consider energy release during failure, as sudden release can be dangerous. Safety factors are used in engineering to ensure structures and components operate well within safe limits. A safety factor is defined as the ratio of the braking stress to the working stress. Values greater than 1 account for uncertainties such as material defects, unexpected loads, and environmental effects. For example, lifting equipment may use safety factors of 5 or more, while aerospace components may use lower values due to strict quality control and weight constraints. Selecting appropriate materials is a key engineering decision that depends on properties such as Young modulus, density, strength, and cost. Steel is commonly used for its high stiffness and strength, while aluminium is favored for its low density in transport applications. Modern engineering increasingly uses composites, such as carbon fiber reinforced polymers, which offer high strength-to-weight ratios. Engineering structures, bridges, buildings, and aircraft, common exam calculations and problem-solving strategies, use of graphs, charts, and data in engineering physics, summary and A-level exam preparation tips. Engineering physics principles are evident in large-scale structures such as bridges, skyscrapers, and aircraft. Bridge cables experience tensile stress and must remain within elastic limits under variable loads. Buildings rely on materials with suitable stiffness to limit sway and deformation. Aircraft structures demand materials that are both lightweight and stiff, leading to advanced alloys and composites. By applying stress, strain, and Young modulus calculations, engineers ensure safety, efficiency, and durability. Engineering physics exam questions often involve multi-step calculations combining stress, strain, and Young modulus. Successful problem-solving requires careful identification of known and unknown quantities, correct rearrangement of equations, and consistent use of SI units. Drawing diagrams and annotating given values can reduce errors. Graphs and charts are central to engineering physics, particularly stress-strain graphs. Students must be able to plot data accurately, identify linear regions, and determine gradients. Data tables often provide material properties, requiring comparison and interpretation. Understanding uncertainties and error bars strengthens analytical skills and reflects real engineering practice. Engineering physics connects scientific principles with practical applications. By understanding forces, materials, energy, and technology, engineers can design safer, more efficient, and innovative solutions for the future. Thank you for watching.